So, good evening and thank you for joining us this evening. You are very welcome. My name is Angus Armstrong and a member of the CED Executive Committee, and I organise these tech talks. I'm not your speaker tonight, that's Mike. All our talks are recorded and available on CED's website and our YouTube channel, and this one should be available shortly after today. This is the third in this season's Tech Talks, which I hope you will find very interesting. Tonight's talk is presented by Mike Yallop. His experience spans over 40 years as a chartered water engineer, working on small to multi-million-pound projects across the world, in Uzbekistan and the West Bank to Japan and USA. He's worked in design and site supervision and has also been involved in the drafting of relevant European standards. So a high caliber guy, and we are, now he's retired, and CED is very fortunate to be able to draw on the depths of his experiences. This evening's talk is titled Compare and Contrast Different Water Pumps. So do join us for later talks, all on the third Thursday of the month at 7 o'clock. And if you'd like to be added to the mailing list, then drop me an email. So I'm now going to hand over to Mike, who will do our presentation for tonight.
Okay, hope everybody can see it. This is in Gulu. This is one of the major reasons I got involved with CED about water. This is a school in Gulu, which was a boarding school, over 1,000 pupils, and that is how they used to get their water. We got it sorted out with CED with the help of Dick and quite a few others. And this is why I got involved. This is, again, a visit I made to Tanzania. This is a well that people were drinking from because their boreholes weren't working, and that's what the people were drinking. This is just quick why I am involved. Now, CED uses basically small pumps. I'm not going to go into all the big pumps and, you know, multi-case pumps and things like this. But basically a pump, as you can see, is a means of transporting fluids from point A to point B. Essentially, no matter how you look at it, there are only really two sorts of pumps. Positive displacement pump, which I suppose in many ways is very similar to a bicycle pump. It's a piston going up and down, or something similar, a screw or something, which forces water through a pipe. The rotodynamic is slightly different because this is by putting, sort of spinning a rotor of some form to increase the pressure of the fluid to force it through the pipe. It's called a centrifugal force, but you can call it all sorts of things. Again, this is a quick summary. The helical rotor pump is, again, it's a screw pump, but it's still positive displacement. It's used quite a lot. You'd be surprised where it's used. It's used where you want to process, you're not quite sure sometimes what the head's going to be on it, and also it's very good at pumping more thicker fluids without much problem. And also you don't have to be so accurate with the design of the pump and the head that you need, because it's very tolerant. The faster you spin it, the more more power you put in, the higher the head it produces, and it's relatively easy to do, but they don't like sand. Centrifugal pumps, well, we all see them. It's basically a spinning rotor. Water comes in, it accelerates through the spinning rotor, and yeah, it just, the more power you put in, the faster it spins, the more water you get out of it. A normal borehole pump is multi-stages of these. When I started looking at pumps, I just realized what an enormous subject it is. But you know, we're only going to look at one or two of the pumps that you can use. Centrifugal pumps, needless to say, to a certain extent, rotary pumps, which include helical rotor, and reciprocating pumps, which are, you'll see, the type we normally use in many, many places. Again, this is just a summary of the types of rotary pumps there are. I'm really not going to get into all of this. We could go on for days. Now, this I'm trying to show you is a vertical displacement pump. Basically, these are tubes with something rotating inside. They're used a lot for when you're doing chemical dosing and so on, particularly that sort of, it's a flexible hose, a rotor goes round inside, and they're used, you'll find them in use a lot. Bigger ones, up to about 3-inch, 75 millimeter, you might find in sewage works pumping sludge, but you know that those are the types you will quite often see as one of the types of pumps you see. There is the other one, which is a screw pump, which we will come in again. There are lots and lots of different types, but that basically screw is a progressive cavity. It's a screw that just pushes it through. They're very good. They do wear with time, but there's very little black flow, and it's a totally constant flow. You don't get poof, 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 which you can get with some of the piston pumps. Now, these are positive displacement pumps. These you will find all over, well, everywhere really. These use, probably the old village pumps were like this. It's a borehole. It has a rising main. This section of the borehole has to be sealed, otherwise water will get back into it. And this is very much like a bicycle pump. The piston goes down, and when it goes down, when it comes up, it sucks the water. When it goes down, it pushes the water up the tube and up the tube. So every time you pump the handle up and down, you get a squirt of water. This is the India Mark II. There's the Afria. They're all over Africa and everywhere else. But this one is slightly different. This is a helical rotor pump. This time you crank the handle. And when you crank the handle, you get a steady flow of water. The pump rotates, and the faster you crank the handle, the faster the water flows. This is a slightly different pump. It's really a Finnish pump. You do find them around quite a lot, and they're very easy to install actually, because they usually come as a complete unit, which you just sort of get the right length, and it squeezes the water up. It's slightly different. You squeeze this, and that squeezes it. Oh, sorry. You squeeze this with that handle, and that squeezes the diaphragm, which forces the water up. They're, you know, usually they're very good actually. I'm not very good at this, I'm sorry. I haven't done this for a long time. And there is an Afri. I mean, you see them all the time. You pump it up and down. This area is incredibly important. Always, when you put a pump in, you must, when you put a borehole in, you must seal this area, and you must seal it down to the rock, so that if there's any pollution coming for animals around, because people quite often bring animals up to drink from this, and it must be really well sealed. The danger of getting pollution in any of this sort of pump is if you don't have a proper seal on the top of the well. This is how a well is normally constructed, and this is what I'm talking about. When you drill a well, you drill a larger size initially down into the rock, and you grout that area. Then you put a simple plain casing in, which is these days PVC. Years ago, it used to be galvanized steel. You have slots in it, which are about 0.8 of a millimeter. These screen slots, well, they've got to be below the water level. And this shaft is incredibly important, because when you drill a well, you're drilling through rock. And when you drill through rock, if the rock's solid, you don't get any water. You only get water where the ground is fractured. It might be layers of sand or fractured rock. And if you don't line the well and gravel pack it, then in relatively short time, stones and bits and pieces will come in, and you'll block the pump and you won't be able to get it out. Also, always remember, when you put a pump in, always put a cable or something onto the pump with a lot of extra length on it, because you don't want to pull a pump out or put a pump in, pulling on the cable or its tube when it's an electrical pump. Oh yes, I forgot to say this. When you drill a well, the driller uses mud. That's to lubricate the wellhead, the drill head. And when he hits water, he knows, because the mud changes, and he can get a pretty good clue how much water is coming out and where it is. But obviously you want to drill below that point a reasonable distance, maybe 10 or 15 meters. Some people make the mistake of drilling a well. Oh, I've got a well, I'll put a pump in it. No, that's the biggest danger you can do, because A, you've got to get all the mud out, and B, you've got to protect the pump from the debris that will come out of the pump when you do it. This is a classic example of what happens if you put a pump in to a well that's not lined and hasn't had all the mud taken out of it. This is a small 4-inch pump impeller, and that's just chock full of mud. It just blocked the pump solid. Sorry, I'm switching between things a little bit. I don't really want to do that one. This is a borehole helical rotor pump. As you can see, you have a motor, the helical rotor there. You have the voltage down here, bearings, and it can be quite a short pump, because that's all the pumping area. Then you have the casing and everything else. That's really just, most of it's just basically a casing to protect the motor, the control systems, the electrics, the bearings, and everything else. The water comes out here, and I like them. Now we're going to a centrifugal pump. Again, we are looking at this area. We're looking at multi-stage, but not just simple, close-coupled single pumps. Again, we're talking about, really, we're looking at a vertical pump submersible well. There are different types, but essentially they're all the same. Now this is, oh God, sorry, I haven't done this. This is how a centrifugal pump basically works. It's a spinning impeller. Water comes in through the eye. It's accelerated by the vanes, and it fires out through here. This is a standard impeller. I'm not going into, there are 3 different types of impellers, but this is the one that we always use. We don't use mixed flow unless you're doing sewage. You don't use the propeller type, because that's for big jobs. And that is how a submersible pump, you will see. It's one, two, this is quite a short one. Similar to the helical rotor pump, you have a motor, casing, control systems, but this time you have pump impellers. Depending on how much flow, I remember these are only usually about 4 or 6 inches in diameter. One pumps to the next, to the next, to the next, and then out. Very important, the non-return valve. Because if you haven't got a non-return valve, I always like to have one at the top as well, but it's another matter. If that doesn't work, then when you switch off, all the water in the piping tank runs backwards, and this pump can spin. This is what we call turbine, and this pump can spin rather a lot and do some damage to your bearings. This is just a quick comparison of the different pipes. We've been looking at a standard, pump, but this is a slightly different type of impeller because it's much more open. This is what you'll be using for sludge, and not sludge, sewage, and it's not, you don't normally multi-stage it. This would be like your flight pumps that you see all over the place in pumping sewage, usually a single stage, not particularly high lift. And this, of course, is an axial flow pump, which is essentially like a ship's impeller. These are for really big pumps normally, normally for clean water. I mean, the biggest one I've ever put in is 5 meters in diameter, but each one of these moves at a slower speed. These will be running quite fast, maybe 3,280 RPM. These probably be running at probably about 1480 of their hours, and these will be running slower. The bigger the pump gets, or even on these, if you're putting bigger pumps in, the slower you go, because you're worried about the tip speed. If the pump goes too fast, then you start getting bubbles on the end of the impeller, and that's when you get cavitation, which is something you should avoid. This is a cross section of a split case pump, which is usually a single stage, motor out here, and this is what you use for when you get into pumping stations. Usually, these are about anything up to about 300, 400 kilowatts, but normally they start for about 20, 25 kilowatts. But we in CED are not using anything that big. But this is how you see them in a pumping station. All of these, that is a sewage pump, that is a drinking water pump. They're just slightly different impeller designs, but it's important you get the right impeller, the right design for what you're pumping. Clean water, you don't have problems. Even then, you should put a strainer on the end of your suction. This is again a section showing how a multi-stage pump works. I hope I'm not going too fast, but again, it's an impeller feeding an impeller, feeding an impeller, feeding an impeller, which is, well, how you get higher head. But there are disadvantages of multi-stage. Every time you put a stage in, your efficiency drops, because the efficiency of each impeller, if this is at 85%, then this is 85% of 85. This is 85 of 85. Once you get to quite a few stages, you get down to about 50%. So, it's something you always have to look at when you do multi-stage. This again is just showing you a multi-stage borehole pump effectively. This is a bit bigger. I have put one of these in a multi-stage like this in a water treatment plant, but you don't normally do a submersible pump for this sort of thing. It's exceptional. It's only if you have a big well. Again, in a system, a lot more system, you might have half a dozen wells feeding into a system, then through treatment, then into storage. This is one I put in Romania, actually. But this is getting larger. This is a typical mixed flow. This is a sewage pump, effectively. It's a bigger diameter, but the principles are all the same. It's a different type of impeller. You don't very infrequently multi-stage it. It's a much wider open vein, and it's very, very, you can get some reasonable sizes stuff through it, but it's still, you need to have screens in front for sewage, because these pumps won't take bricks or quite a few things that come down. So you usually need a screen in front. This is a propeller pump. These are very high flow. No, these motors can be up to 5,000 kilowatts. So we're not really interested in those. Now this, I'm now moving on to solar pumps. This is one of the dangers, and people don't realize over the day, this is over a normal day, this is how your power varies. So when you're choosing a solar pump, you've got to put a line through here somewhere, because that's the flow you're going to get. Your pump will be designed for here. So you have to have a pump that will take variable flow. If you don't have a pump that takes variable flow, and the flow is usually the pump goes faster and slower with solar energy. The more, these pumps are either DC or AC. Oh, I'm sorry. These pumps are either DC or AC. And this is a pump curve, and you see the efficiency drops away. And what you do is you get a series of curves as the pump goes slower. So the efficiency drops a little bit, and the head drops away. So you've got to design your pump so it works within an area. The difference here is with a helical rotor pump, because basically, depending on how much power you put in it, it'll just keep on producing different heads, different flows, but it's very tolerant. And if you put less power in, then it goes a bit more slowly. Well, each turn will produce half a litre or whatever the flow, the size of the pump, will produce so much water. So the slower the pump goes, it still will pump the same volume of water every time the impeller turns. It'll always produce the same head effectively. Just as the energy drops that you put into it, it goes slower. And as it goes slower, well, so it goes slower. It just doesn't pump so much water. So you get, it can tolerate this very well. Centrifugal pumps can do as well, but they're much more complex to design. Now this, again, we're going to pumps. When you buy a pump, particularly slightly bigger pump, the manufacturers make one casing. They only make one casing to each of their size. Maybe it's a 2-inch, 3-inch, 4, 5, 6-inch pump. They all make it. They make one casing. And all they do is you trim the impeller. They'll make one impeller. You get a maximum diameter of the impeller and a minimum diameter of the impeller, which will work. And the efficiencies are pretty uniform. It's just how much they flow. There's a little bit more if you trim a impeller a lot. It's slightly less efficient because you get a little bit more water spins back. But again, this is how you get a typical curve. And this is something you also have to watch. The maximum head against a closed valve, because it's not unknown for a pump to start against a closed valve. And you've got to make sure your pipe work can take that pressure. If you don't, well, you might have the odd problem. But again, you're always trying to get, so you're going to look at your head, and you're going to want the flow, and you're going to try and pick an efficiency point here. On centrifugal pumps particularly, you have to be careful what's called net positive head, because there's a differential pressure in the suction of a pump, obviously, otherwise water wouldn't go into it. So the more, well, people like suck, but the more you suck, the lower the pressure on the suction side of your pump. And if you suck too much, the water actually starts effectively boiling, and you get little bubbles appear on your impellers, and that's what's called cavitation, and that wears them away quite quickly. It does on ships' impellers too if you get them wrong. Now, I'm showing a bit more about the sort of pump curve you get depending on which. These are the three basic types of centrifugal pumps. This is a conventional centrifugal, and you notice that's running generally faster, but as it gets bigger, you slow it down. That's your efficiency curve. You know, that's flow against efficiency. And this is the one you've got to really watch, because people don't realize if you put too big a pump in, then when you start moving down here, you're getting the flows. The pump was designed, you know, for 90 meters head and a flow of, you know, and if you start getting down here, and so you're getting too much flow, the energy you use goes, ooh, and you'll find that it either trips out or burns the motor out, one or the other, if you haven't got the right controls in. These are different. This is obviously a mixed flow pump. They have different characteristics, but you have to watch this bit on those, because the way they work, they power drops away on these, so it's not so bad. But you have to watch the MPSH. You've got to keep yourself down here, or even down here ideally, so that you get the proper efficiency, because again, you've got a risk of this sort of pipe. If you get up into this area, you're going to get cavitation. It's going to be what we call snoring even sometimes, you know. It's not what you want. This is a typical propeller. You're not going to be using them, but you notice the speed characteristics are different on each one. Now, this is very, very, very important, particularly in boreholes, to get the head and the power that you're going to get for your pump. You have two things, and it's very, very, very important in a borehole. You have the static water level, and you must pump test it. And the dynamic water, as you put more water come out, you get to a steady state. When you test a pump, you'll test it at different flow rates, you'll measure the level, and you'll get to know what is this, you know, what is the maximum level you can operate at. Actually, you need a little bit in hand because wells vary during the year, but it's very important that you find that point and you find that point. Because if they're dramatically different, you've got to watch run out. You can't actually start the pump without it tripping things. So the head, the total head you have is the head between the dynamic level and the top water level, wherever you're discharging. This is important. So you have to do the head loss, the friction loss is the friction loss above the ground, the friction loss to wherever your tank is above on the ground, and the friction loss in the pipe. All of these pipes are different sizes. That's not necessarily quite. So sometimes your riser pipe might be only 1.5 inches, and then you'll pump into a 3 or 4 inch, depending on where you're pumping. But it's very important you get to know what your operating head is. From that, when you know the efficiency of your pump, you can calculate what the horsepower, what kilowatts you've got in. It's a very simple little calculation. It's really head in meters, G, flow in cubic meters per second, divided by the efficiency as a decimal. The more stages you have in the pump, the lower the efficiency. That's just how things are. But you have to try and calculate the hydraulic gradient for each of these sections, allowing for bends and everything else. Sometimes you also have a look at the pump when it starts. Sometimes you have to start the pump against a closed head, because you can get, where I was going back here, into this run out condition. So it's very important you keep an eye on. If there's not a big difference, it doesn't matter. But I have done some wells where you may be 200 and something on meters down, and the static waters level is quite high, but when you get down to the actually operating level, it's quite low. So you have to be, keep an eye on it. Now, this is a typical pump curve that you will get for a borehole pump. Each stage, and you'll see the number of stages. So that's 1 stage, 2 stage, 3. So you get a pump curve for each of the different stages. It's not unusual to have 8 or 9 stages in a pump if you need that head. This is a Grundfos curve. It's an American curve, but it doesn't make much difference. If you want 200 meters of head, then you're going to need probably a 7-stage pump. And from then you can get the power curves and the efficiencies for what you're going to get. But it's important to understand that there's a pump curve. Each stage produces a secondary pump curve. And this is how you would select. You want 60 meters, you go across here. You want a flow of 18 cubic meters an hour. Well, then you're going to need an 8-stage pump. And then you can come down here, see the MPSH, and see what efficiencies you're going to be getting. This is getting just emphasizing what I'm talking about. A very simple diagram. You still need power even against a shut-off head. People don't realize that, and that's just power versus flow. Again, you're going to try and always keep yourself into that area of the curve. It's just a little sketch, but you have to be careful. You see this rising, and quite often that's rising, and you'll get yourself into real trouble. This is a cross section now of a helical rotor pump. Whether they're vertical, horizontal, whether they're in a borehole or not being a hole, that is the area. It's just a screw. It can be quite a long screw. Some of them, it can be, depending on the design and what you're trying to do, what head you're trying to get. But basically, it's just you're just turning the screw within a rubber stator, and that's rubber thing there is the thing that will wear if you've got any sand coming through, and that's the danger of these pumps. This is how you would see it in a borehole. A multi-stage pump, seal, gear reduction motor. Again, you have a gear reduction in these to slow the pump down because they don't like whizzing around very fast. They run quite slowly, and it's important you remember that they do run quite slowly. I'm going a bit fast, don't I? Sorry, I don't know how I'm doing for time. A bit faster than I expected. This is a typical pipe that you will be getting up. This is a pipe we laid, polyethylene. Great believer in polyethylene pipe because it comes in rolls. And you use these pipes, ideally when you put a borehole in, you use polyethylene pipe because you get 100-meter rolls. That means there's only one joint, and keep number of joints down, less leaks, and easier to do. And that's how it comes to get it delivered. Now this is just sort of, again, I've been going on about wells because that's what we do. And when you do a well construction, this is what you should do. Tender the works. In other words, get a good specification. Specification should state how he drills it, how he develops it, the lining, how he cleans it. Develop means clean it out. Then you agree that. The contractor, when he drills, should make a log of what he's found on every layer. He should keep samples from each layer so you know what you're going through. You need to know that also because to start with, you do it wider and you go down until you hit the rock and you go into the rock a little bit. Then you go down a size and you seal that area. Again, I say this is how far you should drill. Once you've found the water, you'll find the water, the mud changes. And therefore, yeah, you give it a guess. He gets a pretty good guess because he knows how much mud is pumping down. He knows how much is coming up. Again, this is so important. You clean it, you line it, and you clean it. Then you do what I said before. You do a pump test. That's where you adjust, you find out what the water level is. Sorry. You find out what the water level is and how much water will be coming out. And then that is the thing at the bottom. You cannot select your pump until you've done all of this. If you try or select your pump before you have, and before you've done this, and before you clean it out, you're going to get yourself into trouble. This is a fundamental point. You cannot select a pump for a borehole or well until you've done this, or you'll get yourself into deep trouble. The Hydraulic Institute, if you want more, a wonderful address in the States, is absolutely superb. They have all these different standards. Actually, I've got them all, but that's another matter. And they tell you how to do everything, how to design this. If you were doing wastewater or a bigger pumping station, how far the pumps should be apart from each other, how big the well should, the wet well should be. Absolutely brilliant. Not cheap, but good. I think, I don't know where we're going now. How did I get there? Oh well. Right. Oh well. I must be about the end then. I really kept this to what CED is about. I haven't really, all the stuff I've been doing with them is boreholes or well water, really. And it's very, very important you understand the basic theory, that you follow the rules, you follow them carefully. When I go back to the borehole pumps, basically you have centrifugal, which may be DC, or if there's solar, quite often those pumps are DC, direct current, or they can have inverters in them, so they're AC pumps, and they vary the speed according to the load. Grundfos helical rotor pumps, actually they're rather well. Lorenz makes really good pumps. There are quite a few people out. Grundfos make a very good pump. Their helical rotor pump is very tolerant. There are quite a good pumps where KSB, but you get what you pay for. If you buy a cheap pump, well, it's quite expensive to take out and put another one in, and if you haven't got, that's my opinion anyway. I don't think I've got anything else to say, so I'm going to stop screen sharing. I think I'll press that one and see what happens. Let's try that then. Okay, I'm back. I don't know how long I took, actually. Okay, that's right. 3/4 of an hour. Not far off.
Not far off at all. No, that was really good. We've done a couple of dry runs, and the final presentation, as you put it across, I think that helped me understand things and understand the really important things that you've run through for us. So thank you very much. I'm happy. So you're very welcome to unmute yourself, and if you've got any questions, then bring forward the questions. And I'll kick that off, because there were a couple of things that sprung up for me as we were going through. One of the first question was, you said about the helical rotor pump, that it was very tolerant, and so the temptation would be to say, well, hey, let's just use one of those for everything.
No, first of all, you can't.
Oh, you would say that.
They have limitations on size, and they are not at all tolerant to any form of sand.
Okay.
They're not tolerant to any form of, slightly bit of sand, you get wear on that rotor, and they don't like it. Okay. Yes, they are good. But if you want a higher flow, you're not going to do it with a helical rotor pump, because you can't. You're working sometimes with 4-inch. You've only got 8 or 10 inches to 8 inches to put a pump in. Sometimes 6-inch tube to put a pump in, and you just can't get them big enough. Whereas multi-stage pumps, you can get the flow and the head much easier.
Mm-hmm. Okay. Yeah. So a great pump, but no sand and limited flow.
Yeah, well, you can't, there's a limited size you can do. Yeah. They don't like spinning very fast. So if you want more flow, you've got to make them bigger.
Yep. Okay. And the other thing that I wondered was, I totally see why you want to seal the top of your borehole. And you said the seal should be taken down to rock.
Yes.
But what if we've got substantial amounts of overburden?
Well, you can cheat a bit by putting some clay in first, but you've still got to seal it because, you know, the pollutants above there, rainwater, all sorts of things will so easily get in. You've got a tube, yes, but you've got to really make sure that's properly sealed to the surface because you've got a tube inside a tube, effectively. You drill a larger size with a tube into the rock, then you put the inner tube in, and you've got to seal, make sure that area is properly sealed so the water from the top cannot get in to the well. If you've got animals around, or, you know, you also shouldn't really build a well within 100 meters of a latrine. One of the things I didn't go into was, it's a big thing to me. If you give people water, you've got to make sure they've got sanitation.
Yes, well, that's
something I didn't mention, but it's so important. I mean, I've seen it where we put water in, not in this country, in Egypt, where then people started trying to connect to the pipe. Then I've seen raw sewage running down the middle of the street. It's something you really got to.
So I'm picturing a scenario where you've got 20 meters, say, of overburden.
Yeah.
And down to the rock. And so what you're saying is
you only got about 3 or 4 inches.
3 or 4 inches of what?
The difference in diameter to your ceiling.
So
the tube is into the rock.
So yes. So would the
you're sealing inside the tube?
Yeah. So the annulus between the two tubes, you seal that.
Yeah.
Right. Yeah. So basically, you've got a sealed tube up to surface,
yes,
and then a platform at the top.
Yes, exactly. That's what you're trying to do.
And what are we sealing?
Trying to ensure that you don't get anything from the top into the well. And
that annulus, what are you sealing that with, the grout?
Some people use clay because if you've got a really good clay source and you can puddle it. I prefer to use a grout, but yeah, there's always a risk of grouts cracking. That's why ideally, if you've got a good clay source, you will puddle a bit of clay in at the bottom, because clay is very tolerant and doesn't leak, if you know what I mean.
And there's always the risk, I suppose, if you pour grout down there on top of your gravel packer.
Well, you get it. You make sure you got things right, you know.
Okay. And would you ever be pumping out of a gravel aquifer? So I know right here where I live, people are. Well,
yes, I've done that. Yeah, yeah. I mean, that's not unusual. You might do a well rather than the ground. Whether you might construct a well rather than the borehole, depending on where the gravel is. You know, yeah. I mean, that we didn't go into artesian, did we? You know, there's all sorts of little nuances. When you decide before you even choose where to put the well, first of all, get a decent hydrogeologist who tells you where to drill it. And secondly, do your homework around the area and see what water's coming out. And I haven't talked about testing the water yet, but, you know, it's very important you test the water. I mean, oddly enough, in Romania, in Kurtic, we did some well water there. We had a fit when we tested it. It was 10 times the legal arsenic levels. And we were looking around but people have been drinking that for so many generations. It wasn't from anything or from pollution. It was just natural there. And then we looked around and found the whole area of Hungary was the same, and found out what plants they used for treating the water. It was just bugging some chlorine in enough quantities and you get a powder up. I won't really go into that. But the other thing is, you should test your water. You know, make sure you haven't got something, start doing some water treatment on it. Or, yeah.
I think that's a subject for another talk.
Well, I'm sorry, but
no.
Trouble when you start on these things, it sort of goes into different areas.
I'm making a note. Yep. So I'm wondering if anybody else have any questions for us. What I would say is that, as I said earlier, Mike's presentation will be available on the CED website and will be there for forevermore. And Mike has written a number of chapters of a book, which we hope to host alongside the video archive, so you can delve even deeper for those of you who are sufficiently technically capable of that and interested, which will be a great resource. So thank you, Mike, for allowing us to use that in this way.
Well, I mean, I wrote it for my engineers when we were doing work in, oddly enough, Zaporozhye, Ukraine. But you know, it was a guideline how we could do cost-benefit analysis and so on, because that came up with some really odd results. Results I didn't.
Can I ask a question about the generators used for running a pump?
Yeah.
Am I right in thinking that you need a generator that's got power that's 2 or 3 times the power output of the pump?
Not necessarily.
Started, no.
No, it depends how you're starting the pump.
Right.
If you've got an inverter drive, you can go much closer to the line. But you've got to make sure the inverter matches the pump, as long as you talk the maker. If you're directing DOL, direct online, you might have to go quite a lot higher. You know, maybe 4 or 5 times sometimes, which depends how quickly the pump starts. Because of any electric motor, if you start it, there's a very big power surge. Inverters, that's why people use inverters a lot more. Takes away the power surge. Even modern AC units now have inverter driven, so you don't suddenly get you know, 15, 20 amps, and now you can do it with 5 amps. So it's a matter of how you're driving the pump there, Barbara. If you put an inverter in, then you can use a smaller generator. Simple as that.
Right. I might have to come back to you later with some more details on that, please.
Well, it does depend on the motor and the pump. They've got to match.
Yeah.
We did have one case, case B, I know, where somebody bought the inverter, somebody bought the control panel, and somebody else bought the pump. They couldn't start the bloody pump. Because, you know, it is a balance. The two have got to, that's why you talk to your pump maker. Ideally buy the panel from him if it's a small job.
Thank you.
You see, I mean, go on. Lorenz, for instance, have a control system in theirs where you can connect the power to the solar panel, and as it drops off, it draws more power out of the generator. There are, you know, I wasn't starting to go into the subtleties of that. And Grundfos, their helical rotor pump, will take anything you throw it in it. Because of the way it's designed, it doesn't take a big throw off the generator.
Right.
Sorry, it's not an immediate answer. It depends on the pump.
Yeah. Okay. Thanks.
Going back to what you said about helical rotor pumps and sand, how are you going to stop the sand getting in there? Because I imagine.
Well, you do to a large extent with the screen.
So the 8mm, sorry, 0.8
0.8 of a millimeter, and then P shingle round it, 8mm P shingle is pretty good.
Okay. So if we had some very fine sand getting in, could it tolerate?
No, you know, I mean, yeah, I mean, it depends. You don't want to coarse sand of any sort.
No, no.
But a very fine slurry probably wouldn't affect it, no, because you use it for pumping sludge. You know, there are standard form of sludge pump. You said but you know, it's a case of horses for courses.
Yep.
You get a pretty good get what you're getting when you do your pump test, because you put it into a tank and see what you got in your tank.
Incidentally, Barbara left us there. She'd let me know
Yeah,
she had to leave. She had to leave at 8 o'clock. So
I think she's coming back to me. I don't know where her problem is. I'm sure she'll tell me.
Well, if nobody else has got any other questions, then I think it just remains for me to say thank you, Mike. I know you put quite a bit of effort into preparing for tonight, and whilst we might whip through it in 3/4 of an hour, it probably took at least 10 times that to prepare. So,
Well, I didn't realise how big the subject was until I started looking at it actually, and then had to take so much out.
yeah.
I realised if I really started doing pumps, I'd be on for the next 10 hours.
Yes, that's the thing. So what I'm going to do now is stop recording before I forget to do that.